The outline of this talk is the following. I will start with some preliminaries and motivation, but fortunately this morning we had a great tutorial by Thomas, so I think that they can go very fast through these slides. So this is very cool for me. And after, well, defining what is an Alexandrov space and some basic things about finite spaces, I will introduce a key notion here, which is the concept of the torus-like map and the torus-like multivalued map. After that, I will show you some fixed point theorems, and I will try to use this theory to, well, to try to start the theory of approximation of discrete dynamical systems. Okay, and well, after that, I will show you just a small thing about featured lines of work. So, well, first of all, what is an Alexandrov space? An Alexandrov space is a topological space for which arbitrary intersections of open sets are still open. All right. The interesting thing about this sort of topological spaces is the following. This theorem tells us that the category of Alexandrov spaces where the morphisms are continuous map, and the category of partially ordered sets where the morphisms are ordered preserving maps are isomorphic. And this is really nice because we can treat the same object from two different points of view. On the one hand, we have the topological point of view, and on the other hand, we have the combinatorial point of view. The way to obtain a partially ordered set from an Alexandrov space is written here, and we saw this in more detail this morning. So just the idea is to consider for every point of our Alexandrov space the intersection of every open set containing it. Okay. This is again an open set, and we define the partial order saying that x is smaller than y if and only if ux is a subset of uy. Okay, an example of Alexandrov space. Well, every finite topological space is an Alexandrov space due to its finitude. Okay, here we have an example, and here we have a proposition that we saw this morning. And this proposition is also telling us that we can codify topological information sending to the combinatorial world or using combinatorial terms. Okay, so this is a perfect example about how can we codify, in this case, homotopy in terms of things from partially ordered sets. All right, so well. A way to represent, a very nice way to represent these spaces are with hash diagrams. A hash diagram is a directed graph. The vertices of a hash diagram are just the points of our finite space. We have an edge between 2 points or 2 vertices if x in this case is smaller than y, and we cannot introduce a third element between them. Okay. In what follows, we assume an upward orientation, okay, just to avoid to draw a lot of arrows. So here we have I is smaller than C, B is smaller than B, okay. This example is the previous one. This is the hash diagram of the example of these slides. We can also relate more, given a finite space, we have more structures that we can relate it to it. Okay, this one is the order complex. If we have a finite space, the order complex is just the simplicial complex whose simplices are the non-entity change of x. Okay, here we have a trivial example. On the left, we have the hash diagram of a finite space. And on the right, we have the order complex of this finite space. And we can also, we also have the opposite construction. That is, we start with a simplicial complex and we obtain a finite space, okay? In this case, the finite space is called the phase poset and is the poset of simplices of K ordered by inclusion. Again, we have here a trivial example. On the left, we have a two-simplex, and on the right we have the hash diagram related to it. Okay, the hash diagram related to the phase poset of this two-simplex. So we have these two constructions that goes from finite spaces to order complex, to simplicial complex, and from simplicial complex to finite spaces. The interesting thing about these constructions is the following, that was also mentioned this morning. Here it's very long, the statement of the theorem, but essentially what it's saying is that the homology groups and homotopy groups of a finite space and its order complex are the same. Okay, and we also have exactly the same result for the other construction. That is, the homology groups and the homotopy groups of a simplicial complex and its phase poset are again exactly the same. We have these facts about finite spaces, and we can combine both constructions. We can, if we start with a finite space, we can consider the order complex, and after that we can consider the phase poset, and this construction is called the finite barycentric subdivision. Okay, here we have an example. Consider the finite space whose hash diagram is this one on the left, and the finite barycentric subdivision is on the right. One way to see this finite barycentric subdivision is as follows. The finite barycentric consider the change of this space, okay, of X, and order the change using the inclusion. The resulting poset is the finite barycentric subdivision. And if we consider this point of view, we have a natural map from the finite barycentric subdivision to the original topological space, which is given by this formula. As I said before, a point here is a chain of X. So we can send this chain to the top element. This is well defined, it's continuous, and it has nice properties that we will see later, okay? So the interesting thing about this construction is that we can iterate, okay? So we start, for instance, with a simplicial complex, we consider the phase poset, and we start to consider the finite barycentric subdivisions, and we have continuous maps from the bigger elements to the lower elements. Okay, all of them are continuous. So what we have here is an inverse sequence. An inverse sequence is just a diagram with a sequence of continuous map, a sequence of topological spaces and continuous maps. Okay, this is an inverse sequence. Here we have an example. Is assume that we consider the unit interval and we consider the standard triangulation, two vertices, one edge. Here we have the phase poset of this simplicial complex, and we start with this construction. We consider the finite barycentric subdivision, we consider again the finite barycentric subdivision, and we have continuous maps between them. All right. The interesting thing about this construction is the following. Despite the fact that finite topological spaces in general do not have good topological properties, they can be used to reconstruct simplicial complexes. What we have here is that given a compact simplicial complex, we can reconstruct the homotopy type using this inverse sequence. The way to do it is with a process which is known as inverse limit. I'm not going to enter into details about this construction, but just keep in mind that we have an inverse sequence, okay? And with this inverse sequence, we can construct a new topological space, which is essentially this new topological space uses the previous one and the continuous map and the continuous maps, okay? So this construction is a big space, and in this big space, we can see that there is a homeomorphic copy of K inside this big space, and even more, is a strong information retract. So with finite spaces, we can reconstruct topological information of a compact simplicial complex. We also have a general result, which is somehow very similar to this one, but instead of considering a simplicial complex, we can obtain a similar result for compact metric spaces. Okay, but the construction is not the same, but the result can be also obtained with finite spaces. From my point of view, this is the construction to get these results more geometrical or has a more geometrical flavor, and I think that this one has a more combinatorial flavor. Okay. Now we have almost all the ingredients to start with the main topic of this talk. Well, here we have the definition of the dynamical system. It's a well-known definition, so I will not spend here too much time. But now what I would like to show you is the main goal of this talk, or the main goal of this work. A picture is worth 1,000 words. So this is our main goal. Let us assume that we have here a simplicial complex and we have a homomorphism. Okay, this is a discrete dynamical system. We have seen that this space might be approximated using an inverse sequence of finite spaces. So again, I can put the same inverse sequence to approximate x. Since we have a homomorphism from x to x, I can use exactly the same inverse sequence to approximate x and to approximate x. We know that this inverse sequence reconstructs topological information. So what we would like to have is morphisms from each level of the sequence. What we want to do is to study dynamics for each level, and this dynamics should be simpler because our ground space is a finite space, which is easier than this one. We would like to obtain something like the previous result. Studying the dynamics of these levels give us information about the dynamics of our original dynamical system. So the main problem is, okay, we have to get a definition about what is a dynamical system for a finite space. If we try to adapt, or if we try to use the previous definition, the classical one, we get that, okay, if you consider a continuous dynamical system on a finite space, then it's trivial. So we are in troubles. And if you consider a discrete dynamical system, then you have this result. So after some iteration of your dynamical system, you get the identity, all right? This is due to the finiteness of our space A. So we cannot apply the usual definition to this setting. Then the solution is, okay, if single valued maps do not work good, the solution may be to consider multivalued maps. And this is exactly what we want to do, consider multivalued maps. But the problem is that not all of them are interesting. We know, for instance, in topology, not every map is interesting. The interesting maps are the continuous maps. So here we have to find which class of multivalued maps are interesting for our purposes. Now I will give you the definition which plays a central role here, which is the definition of a vectorized-like map. If we have a continuous map between two finite spaces, we say that F is a vectorized-like map if every chain in Y, for every chain in Y, we have that this set is a cyclic, right? Where by a cyclic, I mean a topological space is a cyclic if its homology groups are the same as the homology groups of a point. So this is our condition, and this is the class of maps at the moment that I will consider vectorized-like maps. Examples, well, we have that every homomorphism is a vectorized-like map. And indeed, what we have is that if we consider a continuous map from X to X, it's a vectorized-like map if and only if it's a homomorphism, all right? So homomorphisms are examples of vectorized-like maps. The interesting thing about these maps is the following. when we apply the homological factor, we get that these maps induce isomorphism in homology groups. All right. So this is really nice, and we can study some of its properties. I mean, we can check, or we can study if the composition gives again a vectorized-like map, that sort of things. Okay, so we can try to study some other properties. I just list here some of them. And now we have the interesting definition. The definition of a vectorized-like multivalued map. A vectorized-like multivalued map is, okay, a multivalued map, you consider the graph of this multivalued map, and there is two natural continuous maps, okay? The projection onto the first coordinate and the projection onto the second coordinate. When we require that the projection onto the first coordinate is a vectorized-like map, then we say that our multivalued map is a vectorized-like multivalued map. You will see in a moment why it's important to consider that the projection onto the first coordinate is a vectorized-like map. It is important for the following reason. We want that these multivalued maps induce morphisms in homology. So the way to do it is to induce a morphism in homology is, okay, the projection onto the first coordinate is P, right? And we say that P, or we impose the condition that P is a vectorized-like map. And previously, we have said that vectorized-like maps induce isomorphism in homology groups. So I can consider the inverse of P, and then I can compose with Q. So this gives me a well-defined morphism between the homology groups of X and the homology groups of Y. So this is the reason why vectorized-like maps are important, all right? Well, some examples of vectorized-like multivalued maps. Well, if we consider continuous maps and we see a continuous map as a multivalued map, then this map is a vectorized-like multivalued map. So it generalizes the usual, the classical case. A really important example is the following. If we have a vectorized-like map, and we consider this multivalued map, which is just, well, consider the multivalued map given by taking the preimages of the points, then this new multivalued map is indeed a vectorized-like multivalued map. So the interesting thing about these multivalued maps is that they induce morphisms in homology groups. So we can try to obtain some classical theorems, some classical fixed point theorems for this class of multivalued maps. And indeed, this is what is written here. We can define a Lefschetz number. A Lefschetz number is just this number, which is the alternate sum of the traces of the morphism induced in homology. And we have this theorem. This theorem tells us this theorem can be seen as a sort of generalization of the Lefschetz fixed point theorem, but for single volume maps. This theorem essentially tells us that if we have a couple of maps, a couple of continuous maps from X to Y, and one of them is a vectorized-like map, this number is well defined because F is a vectorized-like map, so it is an isomorphism in homology. So this number is well defined, and if this number is non-zero, then we have a point. In fact, we have a point satisfying this condition. So we have a coincidence point. And this is important because as an immediate corollary, what we obtain is a Lefschetz fixed point theorem for multivalued maps. Remember, the way to induce a morphism in homology with a multivalued map is composing. Okay, composing a vectorized-like map and a continuous map. So this is exactly the same situation that we have here. We have two continuous maps from a topological space to the same space. In this case of a multivalued map, we have this situation if we consider the graph. If we consider the graph of F, we have the projection onto the first coordinate, which is P, And we have the projection onto the second coordinate, which is Q. So this is just an immediate consequence of the previous theorem, right? And this gives us a fixed point theorem for this class of multivalued maps. And we can generalize a little bit this theorem. Perhaps I can start with a multivalued map, which is not a vectors-like multivalued map, but if I'm able to express this multivalued map as a composition of vectors-like multivalued maps, then I can obtain the same result. Okay, so this number again will be well defined, and it is non-zero. I have a fixed point. But unfortunately, not every multivalued map might be expressed as this composition. It would be really nice if it were true, but it's not true. So don't forget our original goal. Our original goal was to approximate some dynamical information or to start to develop a theory of approximation. I will recall that we have this inverse sequence, which is constructed considering the finite barycentric subdivision. And we have continuous maps between them. Well, the continuous maps that we have are vectors-like maps. And even more, they induce the identity in homology. All right. One of the previous properties that we saw was that if we have a vectors-like map and you consider the multivalued map given by, okay, consider the preimage of every point, you get again a vectors-like map, a vectors-like multivalued map. So this corollary is telling us that we have a way to go back. If we have this map H from x1 to x0, then we can consider the multivalued map that goes from x0 to x1. So this is telling us that we can go back, and in general, this is not trivial. Sometimes the only interesting map between a finite space and the finite barycentric subdivision is the constant one. We don't have more. So this is really nice because we can, as I said before, go back. If we have a continuous map, using the simplicity approximation theorem, we can construct an inverse sequence where these maps depends on the original map, right? Using this inverse sequence and the previous inverse sequence, we are able to construct for each level a vectors-like multivalued map. And the idea is pretty simple. We start here, we move to the left, and now we are here, okay? So we can consider the multivalued map that goes back, like I said before. And if we compose this map with this multivalued map, what we obtain is a vectors-like multivalued map. So for each level, we have a well-defined multivalued map. Now what we want to do is to relate dynamical information of our original dynamical system to dynamical information of the levels of the levels of the inverse sequence. So here we have a first result is telling us that if the Lefschetz number of f is non-zero, then for each level of the inverse sequence, we have a fixed point. Working a little bit more, we can obtain the following theorem. Okay, this is a long statement. Essentially, it says that we have a fixed point of our original dynamical system if and only if there is a sequence of fixed point for each level of the previous construction. We can see this in a picture, and the theorem is telling us that, okay, I have here an inverse, a fixed point if I can find a fixed point for every level of our inverse sequence, and even more, the fixed point should persist through these maps. So there exists a fixed point if here is if this one is a fixed point, and at the same time this this is the image of a fixed point for this level, and at the same time this is an image of the fixed point of another level. So this is telling us that studying fixed points here is somehow the same as studying fixed points for each level of the inverse sequence. A trivial example, let us consider the symmetry through the x-axis. Okay, the symmetry has two fixed points, and we can apply the previous construction. We consider the phase coset of a triangulation of this topological space, and we consider the finite variable intersect division, and so on and so forth. Okay, and we can construct for each level a multivalued map, and we can study fixed points for each level of this inverse sequence. The interesting thing is that from this level, well, in this case, for this discrete dynamical system or this multivalued map, what we have is that there are only two fixed points. For the next level, we have again only two fixed points, which is in concordance with the situation that we have in our original discrete dynamical system. So one of the goals is generalize these constructions to a more general setting, because our starting point is a simplicial complex. So we need a triangulation, and we need to use the simplicial approximation theorem to get this construction. We want to get rid of the simplicial approximation theorem, and we want to apply these results to compact metric spaces, to dynamical systems defined on compact metric spaces, general compact metric spaces. And that would be great because, as I said before, there is a construction to reconstruct compact metric spaces using finite spaces. And this construction has a more geometrical flavor, and it can be implemented in a very, well, I'm not sure if easy way, but it can be implemented, okay? More things that can be done. Well, we have a problem with these multivalued maps. In general, the composition of aviatories-like multivalued maps is not aviatories-like multivalued map. But it would be really nice if we can have a category whose morphisms are aviatories-like multivalued maps, because in that way we can apply other factors, and we can perhaps try to apply a Simchak factor in order to get the Conley index, and we can try to apply I don't know other factors that give some dynamical information, and try to reconstruct other dynamical information, not only fixed points. So the main idea is, okay, we need to enclose the aviatories-like multivalued maps in a category. We can do it generalizing the concept of aviatories-like map. We can do it considering what is called span in some literature, or a diagram. Okay, and span or a diagram is just a diagram of this sort, where P is a aviatories-like map and Q is just a continuous map. All right. So if we consider these morphisms, this will be a morphism from X to, oops, I forgot to write the Y, yes. What we have is that spans or diagrams are pretty common, because continuous maps are an example of a diagram. The aviatories-like multivalued maps, again, are examples of diagrams. So they generalize things that happen in the usual setting. And the steps to get a category, well, the first step is to define a good composition. The idea to define a composition is using pullbacks. And after that, the following step is to define an equivalence relation between spans. In this case, the solution is defining a new notion of homotopy. We want that this new notion generalizes other notions of homotopy. We are interested in a new notion of homotopy, for instance, that generalizes the usual notion of homotopy for the topological category, or other notions of homotopy for multivalued maps. This can be done, and we can obtain the following picture, okay, about categories. On the one hand, we have the category of finite spaces. On the other one, we have the category of homotopical spaces. Using the previous idea, we have a new category, which is a localization of the category of finite spaces and the class of vectors-like maps. And somehow, if this category encloses information of the homotopical category, in the sense that if two spaces here are homotopy equivalent, then here are also homotopy equivalent. So it generalizes somehow some notions of homotopy in the usual setting. One possible application of this new category is the following: the topological degree. Let us consider two finite models of a sphere. Okay, if we are in the usual setting, we cannot realize every integer number as the degree of a continuous map between x and y. We have some restrictions, so it is not possible to obtain this classical result. But in the new category, this is possible. Okay, we can try to obtain a more combinatorial description of the topological degree. This is one of the goals of this application. All right. I think that I'm on time. Yeah. Here I have some references. Okay. And well, I think that's all. Thank you very much for your attention.
I have a question. Yeah, so you mentioned, you gave a definition of Vittori's map, just for continuous function of multivalued. Can you give an example of Vittori's map? Because I mean, like from the definition, I couldn't get the intuition of how Vittori's maps behave.
Well, for instance, you have homeomorphisms. Yeah, I know that this is a trivial example. I know. Well, you have this example, which is perfect. This one, okay? This is a continuous map from the finite variable subdivision to the regional space. Okay. This map is a vectors-like map. Okay, we can, for instance, let us consider this check. Well, if we consider A, the preimage of A in this case would be A. All right. Okay. So it is a cycling, or we can consider a chain. Consider this chain A and C. The preimage of the union of A and C give us A and give us also this one. All right. Okay. The pink and green part. Okay. And notice that this is a bitpoint. I'm not sure if you're familiar with bitpoints, or what you obtain is the hash diagram of the resulting space is something like that. And this is contractible. So it is a cycle. Okay.
Thank you.
Thanks. Yeah, sure. Yeah, thank you. So lots of things that you show, I mean, they seem to have quite a strong model category theoretic flavor, especially these Vittori's-like maps. They seem to be some kind of basic vibration, maybe, and something that's done quite commonly in computing. And the theory is taking some object, replacing it with some vibrant object, and that it maps out of this replacement. And these multi-valued maps also seem to be related to that. So my question is whether you have an understanding of this, these terms, or
Not yet. I mean, I'm trying to enter into this theory, a more categorical language. At the moment, I'm just trying to
okay, yeah,
turn that out.
yeah, I think there's definitely something in that sense.
Mhm.
Just to make a question, at some point you told us that you can recover a compact metric space from various matrix subdivision.
No, using a different construction.
I didn't understand.
Yes, we can also recover compact metric spaces. The information. Well, we have exactly the same result for compact metric spaces, but we don't use this construction. We use a different construction. Okay, because this one is for this construction, it's very important to have a triangulation. But if you have a compact metric space in general, for instance, the Hawaiian ear ring, you cannot apply this sort of construction. But there is a different construction that uses finite spaces. So you obtain a finite sequence, an inverse sequence, where the terms are finite spaces, and you reconstruct also you get the same result.
Okay, so my question is then, in which category do you consider the investment?
The topological category.
Together with topological spaces. Questions? So, from the speaker again.